Hi, welcome to our talk on better regularization for sequential decision spaces. My name is Gabriele, and this is joint work with Christian at Columbia and my advisor Tuomas at CMU. So before we start, let me give you a summary of the main results in this paper. As you might know, a Nash equilibrium in a two-player zero-sum extensive form game is a bilinear saddle point problem, that is a problem of this form. Now the sets Q1 and Q2 that appear in the domains of the minimization and maximization problems encode the decision problem that are faced by the two players in the extensive form game. Q1 and Q2 are convex polytopes with a strong combinatorial structure. Now, if the game is large, the most scalable algorithms for solving the bilinear saddle point problem above are first-order methods. However, those methods typically require some form of projection onto the feasible domains of the minimization and maximization problem at each iteration, which in the case of sequential decision spaces can be very expensive if you use the naive Euclidean distance. So for that reason, before deploying scalable algorithms, it is imperative to define an efficient notion of distance onto sequential decision spaces. And such a notion of distance is a type of regularization that is called a distance generating function. Now, when designing a distance generating function, there are several desirable properties. You would want your function to be differentiable, one strongly convex. You would like for the gradients to be computable in linear time, better if in closed form. You would like for projections to be computable in linear time, better if in closed form again. And finally, you would want the diameter of the sequential decision polytopes as measured by your regularizer to be polynomial in the size of the extensive form game. So for more than 10 years, it was known how to obtain the first four properties, but not the fifth. And the way you would obtain the first four properties was by using a class of regularizers that were introduced by Hode et al., which are called dilated regularizers. Now, since there are great guarantees of online mirror descent, and really most first-order methods depend on the diameter of the decision space, that meant that for a long time, using mirror descent or those first-order methods on tree-form sequential decision-making problems meant that the regret bound was sublinear in time, but hiding exponentially bad constants in the size and in particular the depth of the game tree. So with this paper, we fixed that issue by moving away from dilated regularizers a bit, and with now first-order methods with our regularizer can be instantiated in a way that guarantees polynomial dependence on the size of the decision problem, while at the same time simple linear time iterations. So more specifically, by instantiating first-order methods with our regularizers, we develop a practical accelerated first-order method for computing Nash equilibria in two-player zero-sum games that does not hide exponential constants in the game tree size. We also develop a practical accelerated first-order methods for computing correlated equilibria and ex-ante coordinated team equilibria in certain classes of games where those equilibria are known to be tractable. And finally, our methods have a guaranteed 1/t rate of convergence along with efficient linear time proximal updates. So with that, let me offer more details about how our distance generating function works. And first, we need to talk a bit about sequential decision spaces. So consider a player in a simultaneous game like rock, paper, scissors, where there is no such thing as taking turns or reacting to observations. So every time the player plays the game, they have to face whether to play rock, paper, or scissors. And if they're fancy about it, they might end up randomizing their choice. So in that case, a strategy for the player is just an assignment of probabilities to each of the three actions, which is a point in the probability simplex spanned by the three actions. Now, because the player only gets to act once, I'll call this one-shot decision-making. Instead, consider now a sequential game, such as poker. So in a game of poker, the player will take multiple actions, but also make observations such as what hand was dealt to them or what bet the opponent placed. So as an example, the figure shows the decision problem that is faced by the first player in the game of coon poker. The interaction starts at the root, where the decision maker observes their private card, which could either be jack, queen, or king. Suppose that the decision maker observes a jack. Well, in that case, the process transitions to the decision point x1. At x1, the decision maker has to pick whether to check or to raise their bet. If the decision maker checks, then the process transitions to an observation point where the decision maker will observe whether the opponent he is playing against checks or raises, and say that the opponent checks. Well, in that case, the interaction terminates and the decision maker will receive some form of feedback, for example, how much money they won or lost in this game. So to generalize beyond this example, we can always represent a tree-form sequential decision problem as a tree made of two types of nodes. The first type is decision points, where the player has to pick an action, and the second type is observation points, where the player observes something about the environment or the opponent. Now, tree-form sequential decision problems are the problems that are faced by players in extensive-form games, and of course, decision and observation points form a tree. So before we can do anything with these sequential decision problems, though, we need to at least decide how we're going to represent strategies. So in one-shot decision making, like we said, like for example, if you have to play rock, paper, or scissors, a strategy is simply a distribution over the finite set of actions of the player, and that's the end of the story. But in tree-form sequential decision making, the situation is more nuanced. So at first, you might think that the natural way of representing a strategy in a tree-form decision-making problem is to simply assign probabilities to each action at each decision point. For example, you might decide that you want to check 10% of the times and raise 90% when playing at x1, and fold 80% of the times or call 20% at x4. Right, so if you do this for every decision point and then you stack together all these numbers into a vector, you end up with what is called a behavioral strategy. Now, because you're basically stacking together points and probability simplices, the set of strategies is clearly convex. However, the caveat with this representation of strategies is that the expected utility in the game is not linear anymore. Right? And the reason is that the probability of reaching a terminal state now in this representation requires that you take products of the probabilities of the actions on the path from the root to the terminal state. And because you have products, you have non-convexity. So there is a solution to this problem, and that is a different representation that avoids that avoids the need to write products. And the way it does that is by storing probabilities for whole sequences of actions instead of probabilities only for each individual action at each decision point. So to see how that works, we can start from the behavioral strategy that we defined in the previous slide and convert it into this new representation. So what we do is that for every path from the root to any decision, what we do is that we replace the number in green with the product of all the numbers in green on that path. So for example, if you look at this path, then we had that in the behavioral strategy, we would start with probability 1, check at x1 with probability 0.1, and then fold at x4 with probability 0.8. So we take the product of all those numbers and we end up with a 0.08 in that position of the vector instead. We do this everywhere, and what we end up with is what is called a sequence form strategy. Now, if I give you a vector and I tell you that it's a sequence form strategy, how would you check? Now, there are some trivial checks. For example, you would want, of course, all entries to be non-negative. Another easy check is that you want to start the game, so you need that the root sequence has probability 1. And then you have more complicated checks, which go back into this idea of probability mass conservation. So for example, if you look at x4, then you have that the sum of the probabilities of the paths that start from the root and then in all of the actions at x4, like if you sum them, that probability has to be equal to the probability of actually reaching x4 in the first place. Right? So you would want that that 0.08 plus 0.02 at x4 matches the 0.1, which is the last sequence that is reached before actually getting to x4. Right, so because all of these consistency constraints, which you can prove are both sufficient and necessary, basically amount to linear equalities and inequalities, then clearly the set of strategies is convex. In particular, it's a convex polytope. But also because we are representing products directly, the expected utility is now a linear function. Right. But the problem is that Euclidean projection onto these sequence form strategy polytopes is very expensive, which leads to this natural question as to, can we design a distance generating function that is like a different notion of distance rather than Euclidean, so that projection onto those sets becomes easy. Right, so let me talk a little bit about what the state-of-the-art solution before our paper was, and then I'll talk about what we propose instead. So dilated distance generating functions were a solution to that problem that was introduced by Hode et al. In 2010. And the idea is simple. So first you would pick local regularizers for each decision point in the game. And common choices for those local regularizers would include the negative entropy function or Euclidean distance, for example. And then what you would do is that you would stitch together those local regularizers by using dilation, which is a convexity preserving operator. Now, the final form of the regularizer is then something like this, where you would take a sum over all decision points of the probability of reaching the decision point multiplied by a regularization of the local strategy at the decision point times a suitable positive scalar that depends on the decision point. Now, dilated distance generating functions have been the de facto standard in the extensive form gaming literature for more than a decade. And the reason for that is that they have many desirable properties, and perhaps the most important is algorithmic. So specifically, proximal steps, which are like this notion of generalized projections, according to these dilated regularizers, can be computed exactly with a linear time to traversal. So they're way more efficient than Euclidean projection, and they effectively solve the problem that we were talking about earlier. Another reason to like dilated distance generating functions is analytic. In particular, these are Legendre functions, so they are very well behaved and can be used in a lot of contexts. And there is another property that would seem good news, which is the fact that these regularizers can be made one strongly convex by acting on the coefficients. But the reason why this point is in yellow, though, is that to obtain one strong convexity, the coefficients alpha j might need to be exponentially large in the game tree. Right, so this is not ideal because it basically means that the first order methods that are instantiated with dilated distance generating functions will have convergence bounds that hide exponential constants in the size of the game tree in the worst case. That has been the case for a long time now. So this led us to wonder, can we design a regularizer that is practical, which means it retains simple linear time proximal steps, and at the same time does not hide exponential constants? What we show in this paper is that the answer to that question is yes. Right, so while the details are pretty technical, I'd like to shed some light as to what are some of the ideas that make possible our solution, which, by the way, we call dilatable global entropy regularizer. So first of all, it is important to realize that our regularizer is not a dilated distance generating function. So if you remember, dilated distance generating functions stitch together a bunch of local regularizers, but instead our regularizer is much more global. It's not dilated. It has a double sum, the first on the decision point, the second on all actions at that decision point. But the argument of the sum does not have any fraction or any local strategy. So our regularizer looks much more like regular global entropy than dilated entropy. Now, the special feature, which in a way is the biggest idea behind our construction, is that the terms of the sum are actually weighted or multiplied by suitable coefficients. So those coefficients are the fundamental key of the construction. And in particular, they're defined in a way that enables a regularizer to be expressed equivalently as a dilated distance generating function when restricted to the palatable strategies, which we call Q in the slide. Right, but it's important to note that our regularizer can be expressed in this dilated form only when restricting to the set of strategies Q, but not everywhere else. On the other hand, the fact that we lost dilatability everywhere enables us to gain elsewhere, though. So in particular, our dilatable global entropy achieves one strong convexity with coefficients that scale only polynomially in the size of the game in the worst case, and not exponentially anymore. Right? Furthermore, it turns out that actually dilatability everywhere was okay to lose. So in particular, we show that even if the dilatability applies only on the sequential decision space Q, it is that fact alone is enough to retain all the nice algorithmic and analytic features of dilated distance generating functions. Right, which means that we retain simple linear time proximal steps, and also the fact that our regularizer is a Legendre function. So all in all, we retained all the nice properties of the dilated distance generating functions while fixing the only bad property that they had. So it's a win-win. Also, the theoretical superiority of our dilatable global entropy regularizer, which, as we said, does not require exponentially large coefficients, seems to translate into practical wins when compared to dilated distance generating functions, in particular those that use negative entropy as a local regularizer. So the 9 plots in the slide refer to 9 different two-player zero-sum extensive-form games where we computed a Nash equilibrium using the excessive gap technique, which is a first-order method. And the x-axis measures the number of iterations, while the y-axis measures the distance from the Nash equilibrium. So you can see that our global entropy regularizer outperforms the dilated distance generating function consistently in all 9 games. But there is actually a second part to the paper that I haven't talked about yet. And it turns out that the principle behind dilated distance generating functions and behind our dilatable global entropy regularizer generalized to other structured sets of interest in game theory beyond sequential decision spaces. So in particular, we extend both techniques to any set that is obtained by using scaled extension, which is a complexity preserving operation that can be used to capture the space of correlated strategies of 2 or more players, with applications to correlated equilibria and team equilibria in classes of games where the characterization is tractable. So in those contexts, our regularizer once again gives the first practical accelerated first-order method that guarantees convergence to optimal correlated and team coordinated equilibria. And once again, we see that the dilatable global entropy regularizer outperforms the dilated distance generating function, this time on some general sum games with the task of computing normal form coarse correlated equilibria. So with that, let me take a step back and summarize. We've seen how sequential decision spaces have a complex combinatorial structure that makes naive Euclidean projection extremely expensive. And for that reason, it is important to design efficient notions of distance for those domains. Dilated distance generating functions, the existing solution before our paper, were able to achieve many desired properties, but at the cost of hiding exponential constants in the game tree size and in the convergence bounds. But instead, our dilatable global entropy regularizer is able to retain all of those desirable properties while sidestepping the issue that I just mentioned and hiding constants that are only polynomial in the game tree size in the worst case. Finally, we have also seen how both techniques apply to more general combinatorial sets of interest in the theory of extensive-form games, such as the space of correlated strategies in triangle-free games, with applications to team coordination and collusion. In those settings, our regularizer enables new state-of-the-art accelerated convergence bounds. That's it. If you have any questions, I'm happy to answer now or via email. And if you're interested in reading the paper, we have the full version of it loaded on arXiv.